So yeah, let's jump into it. So yeah, we're going to talk about acoustic keystroke loggers. So that's hence kind of the title, The Sound of Your Secrets. And what an acoustic keystroke logger is, like a normal keystroke logger is usually something you install on your laptop or computer. You type on your keyboard and it intercepts and hooks what you're typing to figure out in a malicious way to like understand what you're typing. But this is doing it purely based on acoustic or sound. So we're going to talk about how to build one, and we're going to talk about some of the interesting stuff along the way and how to defend against that kind of stuff. So my name is David vonThenen. I'm an AI ML engineer. I do all sorts of crazy, wild things with AI and ML. So this is one of them. I've kind of talking earlier. I've built machine learning models to detect Parkinson's disease through voice. I've built machine learning models to detect sarcasm, and then non-voice related things. I'm fascinated with small language models, so I've got a ton of things on how to utilize small language models in a cost-efficient way. So there's actually a recording that I did at Devox Greece like about 2 months ago-ish, kind of centered around reducing your cost for inference. But yeah, that's a little bit about me. And here is the agenda. So if you caught the keynote this morning, I thought it was a great keynote, and there was a lot of stuff that actually most of it I agree with. And so the first topic we're going to talk about is the moral duality or the ambiguity with AI and ML. And kind of the reason why I want to start with that is because we're talking about a weird, insensitive subject. I'm literally going to teach you how to build an acoustical keystroke logger. We're going to like kind of decompose the problem so that we can build one out. And yeah, we're going to do a bunch of it via live demos. Obviously not the training, that takes a really long time, but you kind of will do like inference and kind of talk about acoustic keystroke loggers. Then we're going to talk about how to apply this in the real world. Obviously don't do this, but you know, it's kind of understanding like what can happen and how you can apply this stuff, because the next one is we want to talk about privacy, security, and the things you can do to defend against this. And then we'll have some Q&A at the end here. So let's talk about the moral duality of AI and ML. So you probably just open up anything, LinkedIn, Twitter these days, and you have news stories all over the place about the extreme positive and the extreme negative of like AI. And so here's this, taken from Twitter, from Elon Musk. So here's an extreme positive outlook on AI and ML. So Elon Musk is saying, hey, we don't need to worry about universal basic income because AI and ML is going to drop the price of manufacturing and building things. It's going to be so cheap that it's going to be universal high income. Take whatever you believe. I probably don't think that's going to happen. If you just kind of think about it, right? If we can't all build, or we can't all drive a Ferrari, right? There are limitations to resources and how much you can build a Ferrari and all that stuff. So that's probably not going to happen, although it would be great if that were the case. And here's the extreme negative. So here's an MIT study that basically said about 12% of the US workforce can already be replaced by AI and ML. And here's also another article that's saying the number of programmers has plummeted to its lowest level since 1980. And this, I believe, was a Fortune article. No, it was a CNBC article that basically, and they made a distinction between a programmer and an engineer. So like a programmer is just someone that builds code, doesn't engineer a problem, right? Specifications, design docs, how to build a big chunk of code, something that does, an application that does something very, very massive. So this is like the extreme negative outlook on AI. And I think we're going to probably land somewhere in between. So yeah, it's just very interesting to see these two extremes when it comes to this particular subject. And if we just look at the technology itself, forget how we apply it, there was in the keynote, AI and machine learning is doing extremely awesome things. The protein folding, discovering new drug applications, here's this NIH, so the National Institutes of Health article saying, hey, we've used artificial intelligence and applied it in such a way that we're finding new medications and new drugs to like cure diseases we couldn't even think about. And it's pretty amazing, right? And I think we need a lot more of this. So yeah, this is kind of like the technology is amazing, and if you kind of take away all the speculation and everything, it can do massive amounts of good. But if you have people that are trying to apply it in a negative way, so I don't know how it is here. I have yet to go into a grocery store. I kind of do this everywhere I go, just to pick up like odds and ends, water. But in the United States, we started employing digital price tags at grocery stores and all sorts of other retail places. And the reason why is that they are using machine learning algorithms now to maximally extract how much you'd be willing to pay for an apple or for your groceries. And based on the time of day and like a Monday or like a Friday after work, they'll change and update the price of your groceries so that you stop by after work, maybe you're too tired to go shopping elsewhere, and so they'll crank the price up. And so this is the extreme negative of like what machine learning can do, and this is horrific in my opinion. But it is what it is, and I'll also throw out here, just to talk about it. When you go and order stuff on, and like pull up an app to do ordering for groceries, the price on the app is very materially different than what it is in store. So just be aware of that. Make sure, price check. But companies, unfortunately, corporations are doing all sorts of crazy things to extract the most they can from you. So, talking about all this AI, ML, ambiguity, and like the security, and I did not create any of this stuff. So a lot of this stuff was based actually on this archive research paper. So it's a practical deep learning based acoustic side channel attack on keyboards. And I basically took this archive research paper and I implemented it. Whether this is good or bad or not, I made a ton of other improvements along the way to make this more efficient and so that it will work. And so I just want to call out that this is there, and we'll kind of talk later on like why. But it's basically in order to understand, like in order to defend, we need to understand, right? And so having this available for everyone is gives people the opportunity to come up with defenses and ways to mitigate this kind of stuff. So, having said all of that, let's go ahead and build an acoustic keystroke logger. So, an acoustic keystroke logger is really just machine learning audio classification. And believe it or not, this has actually been happening for some time. And if you think about like what audio is, it's just frequency over time. And if we actually take that frequency over time or that audio file, and we actually map it, this is what it actually looks like. Right here on the bottom axis, you have time, and then you have frequency, and then think of this as like a heat map, right? How intense that frequency is at that point in time. And so typically when you're trying to build a machine learning model to attack this type or build a model to classify sound, you typically take an audio file, usually it's a WAV file in linear 16 format. You create a spectrographic image, which is what that image is right here in the upper corner. And that is what we're going to use in order to train our machine learning model, because we can do frequency over time, get the intensity of that frequency at that particular point in time. Now, then how do we classify it, right? So if you look at the picture right below it, each cell is a different sound. And you can see here, like where the pointer is, these two sounds, right, they're different cells. You can even just visually take a look at it and say, hey, those two sounds might be the same type of sound, whereas like the one next to it is obviously a different sound. And so even just visually looking at it, you can make a determination that those two sounds must be very similar. They must come from the same thing. And the third picture there, the third cell, is obviously something very different. And so this has been happening for some time. So like the most basic example, and I provided links to like, so you can take a look at it, or some of them even have examples on how to build it. But like the most basic example is like cats and dogs, right? A cat meowing and a dog barking. You do this method, create spectrographic images, classify the images based on cats meowing and dogs barking, and you can say, this is a cat or this is a dog. So a more non-trivial example. So in certain states, certain countries, and certain cities, there's actually machine learning models that detect gunshot sounds. And they do this in urban settings so that if there's a gunfire, right, you can quickly deploy police to that particular location and have emergency personnel and police respond right away. Now, what's interesting is, right, that besides it being very interesting, is that you need to be able to distinguish from other types of sounds that might sound very similar. So this is like a car backfiring, someone lighting off fireworks. So I live in Long Beach, California, and there are literally fireworks going off every night. It's ridiculous. So you need to be able to distinguish those types of sounds, right? Because you wouldn't want to call the police or whatever, emergency services out because a firecracker's going off, right? So some other cool things you can do with like doing sound classification. So I actually gave this session, this is recorded, so we're not gonna watch the video obviously, but you can use sound classifications to do things like sarcasm detection or detect Parkinson's disease through voice, using a voice sampling. If you're very interested in this kind of subject, I would encourage you to take a look at this. It's just kind of something very interesting and very cool. We're obviously not gonna watch it. So, like with any machine learning problem, it starts with a data set. And there's two data sets that we're gonna use in this session here. So the first one's at the top there, keystroke noiseless final. So this is a data set that was already curated. It was actually used at a hackathon at a Singapore hackathon type event in 2024. And this is actually the most basic understanding of the problem. It's a single keyboard, and we're going to use the sounds, the acoustic signature for that keyboard to do classification to find out what letter I'm pressing. And now the second part is this multi-keyboard acoustic data set. And there's actually a previous attempt, a research paper that tried to bite off this problem, and this is kind of like where the improvements that I've made along the way. But the idea here is we have multiple known keyboards, and we're going to collect the data set sample for every key press on these known keyboards, so I believe there are 6 of them, and build a machine learning model to classify the sound across multiple keyboards. So those are the 2 data sets. Now that we have data, we need to be able to develop a pipeline to extract the information we need out of it. And so basically we take the WAV files, so they're all linear, WAV file, linear 16 format, same speed, I believe it's 44.1 kilohertz, so everything's the same. And then we generate spectrographic images, which is the one on the right there, and we do that and collect it for every key press. Now we need to put them in folders, and we're going to use the folder name effectively to classify the sound. So as an example, if you take all the key presses, right, all the audio for the letter A, you put all that audio into the folder A. You do the same for B, C, and so on. And we generate the spectrographic images, and kind of the important component of this is we have 3 channels that are used in our how we build our machine learning model, and why they're 3 channels, it's because of RGB, right? Red, green, and blue. And then we take the RGB values, and each pixel, we determine how intense. That's how we map the RGB to the pixel that's at that particular time and frequency. And we basically use, through the magic of machine learning and machine learning algorithms, and we're using PyTorch, to build a machine learning model to detect patterns based in these spectrographic images. And then we do a bunch of cool things, because nothing is perfect. You hit a key press, you aren't guaranteed that that key press happens at time 0. Maybe it's shifted a little. So in our machine learning algorithm to train the model, we do all sorts of things like add noise for like robustness, do shifting for time, so that we introduce a bunch of variability, so we eliminate, like we push the button a little too late. And we basically then train the machine learning model and have something to classify sound. And we're using 38 different keys, which is the labels, right? How we classify the sounds. We have A through Z, 0 through 9, space, and enter. So we're going to classify 38 different button presses on a keyboard. So this is the model training algorithm, which is really not important. If you're interested in talking more about this, like after the fact, hit me up for sure. Kind of just really high-level overview. So this is a CodeSnet style architecture that combines a neural network and like convolutional bitwise self-attenuating classifier for images. So kind of like the upshot of that is local patterns and global context. We take little nuances in like frequencies, but we also consider that where those little subtle nuances happen over the entire sound pattern, right, the image. And we do all sorts of weird things, which is reflected in the research paper. I did not invent all this. So an unusually common number of training cycles. We do all sorts of optimization. Really not the point of the session, but if you're interested in talking more about this, I'll be happy to chat with you afterwards, or even when you get home and you're interested in looking at the code. So yeah, let's start looking at the problem. So anytime you have a machine, you're trying to build a machine learning model, and we're specifically talking about classification, and this applies to any kind of machine learning model. So you're going to kind of get like a machine learning 101 kind of a thing if you're not familiar with how machine learning works. You have like a data set, and what we need to do is we need to chop the data set into training data, validation data, and test data. And in this particular case, and in most cases, the way we kind of chop it up, like every problem's different, but we typically do like 80% training data, 10% validation data, and 10% test data. And the training data is obvious. That's what we're using to like build the classifier. The validation data set, the portion to do validation, think of it as using that data to hone the correctness for the machine learning model. So that's what we're kind of like measuring against. And when you hone it, however number of training cycles, out on the other side of PyTorch, you get a machine learning model. Now, the test data, right, another 10%, is what you can use to validate the correctness of that machine learning model. Like how accurate is that model given like 2 or 3 key presses for A, B, C, and so on. So that's literally how we're going to break apart the test data. And instead of just talking about this, which is boring, I'm sure, we're going to actually do it. So I'm going to go ahead and just actually show you what this kind of looks like. So I already kind of like a high-level talk through the data training, the preparation. So we actually have, right, a data folder. And if we go ls data, you can see the training, validation, and test data. And if we actually go ahead, and I'm just going to pick one of them, the training data, I only have one letter, so the letter A. And if we go ahead and expand that out, you can see the different WAV files. So each one of these WAV files is one instance recorded of the sound for the letter A. So there's 1, 2, 4, 5, 6, 8, and so on. So, right, again, the goal is now to take that WAV file that represents the letter A, and we need to convert that into a spectrographic image, right? Frequency over time, a picture that captures that with the intensity of frequencies and all that fun stuff. And actually, if we want to, obviously we have the data folder. I don't have an images folder, but I think it might be just worth taking a look at one of these images. So training data, test A, oh, sorry. So that's like the WAV file, and then we're going to go ahead and create spectrographic images for each one of those image wave files. I can never remember this long command, so I have it right here. I'm sure if I had to type it in manually, it would be ridiculous. But I'm going to plop it in there. And then now we have an images folder. And if we go to that folder, and we look at training data, and we look at the letter A, we just pick the first instance. This is what one of the spectrographic images for an instance looks like. So now that we have a method to extract spectrographic images from all of these sounds, let's go ahead and train our machine learning model. And we're, again, for this first problem, we're going to attack a single keyboard. So this is one keyboard. So we hit the button on this known keyboard, and we are going to hopefully be able to tell whether or not what button we're pushing based on that particular sound. So to train this model, and you don't need to, so I have all of this code, believe it or not, in my GitHub repo, so there's no need to copy this down. You can do this at home. If you want to do this at home and train your machine learning model from these sets of wave files, you can go ahead and type in Python 1.train, and it will train the model. Using an H100, it will take roughly about 12 hours, just as an FYI. Having said that, I don't want you to burn your own cache. So I've created models that are safe tensor format that will work on any laptop. So you can run inference on them. And so that's what we're actually going to do. So we have this model that I'm providing. It's available for download. And we're going to use that model to run inference. And we can actually, just as an example, we have the letter S, and it's instance 9. It's a PNG file, right, representing that acoustic signature for the letter S. And obviously, this is part of the training data. So, right, this is an image that this model has not seen before, right? And if we go ahead and run inference, you can see S, and then the first one is 100% accuracy. So using a known keyboard, a single known keyboard, using the acoustic signatures, training a model, we can, with 100% accuracy, determine that this is the letter S. And that's pretty frightening and pretty scary, right? But yeah, it's very interesting. So let's move on to something slightly more difficult. So that was 100% accuracy with a single keyboard. So now let's move into multiple keyboards. And so that data set that I referenced earlier, it was this particular data set. So I grabbed icons from the keyboards, so Lenovo, HP, Apple, MSI, and then the two on the end are very interesting. It's taken those keyboards and recorded the sound over Zoom and recorded the sound over Messenger. And that should be the wake-up call that if you are typing with your microphone unmuted, beware. I would not do that anymore. Mute yourself, please. But this is the data set that we're going to use in order to train our multi-keyboard machine learning model for acoustic keystroke logging. So this is what the data, this is how we do the dependent data set. So, right, we have to chop everything up. So we have training data, validation data, and test data. So what we do is we want to have sampling for every keyboard in all three of these buckets so that we can have HP and Apple as a part of the training set, and then we use that same validation data, right? Now, other different instances for those sounds for Apple and HP, and we use that to converge the model to learn or to classify these keyboard sounds. And then we also have data, which is not a part of the training data or the validation data, and we use this test data, which we have samplings from all those keyboards, in order to test the accuracy of our model. And so we're doing the same thing, except we're now doing multiple keyboards. So again, instead of just talking about it, let's go ahead and demonstrate this. So we're going here. So 3 train, which which is here, so multi-keyboard dependent data set. And if we go ahead and we take a look at the data set, just so that we have like an idea and understanding, we have the same test, validation, and training data. And if I just pick one of those, let's just do validation. These are the different keys that we're using to classify, right? I kind of already alluded, 38 different keys, 0 through 9, A through Z, space, and enter. And if we go ahead and pick one of those, you can see that's the test data for for all those different keyboards for the letter A. And so if we actually were to do something like look at the test data, or the training data, sorry, and we look at the letter A, right, that's spectrographic images for all those different keyboards. Notice that the data is much larger because we need more data to train and classify. So you have the data set. You use that same script I did before to take the images, or to take the WAV files to create the images. There's a fancy script here, which is Python 1_train. This is a script to take those images in the folder right here and to train that machine learning model. And again, an H100, 12 hours, maybe even a little more later, you have a model. And like I said, I don't want you to burn your own cache. I have, again, just like before, already pre-trained models that are safe tensor that will work on any laptop, no matter what the CPU, GPU, or whatever it is. So we're going to run inference using another key, right? And I've just randomly picked one. So the Lenovo keyboard, the letter H, and then this is sound or instance 5. And we're going to take that spectrographic image and we're going to pass it through that classifier model, and we're going to see what we get. So Python_2 inference. So very different. So we have the H. So the most confident classification is the letter H, which is correct. But notice the confidence score has dropped to 48% roughly. And then the second guess is G at 24% and so on. So this is top K. For those that are, have used like inference for like LLMs and stuff like that, you can specify like top K equals whatever. So this is top K equals 5. And this is very important. Keep that in mind because we're going to use that to our advantage in a second here. But we can get what the top 5 most confident guesses are in the letter H at 48%. So that's very interesting. Notice that it's not 100% like the single keyboard, but we're dealing with multiple keyboards. That's still pretty crazy. So I thought I would create a simulation. So let's go ahead and go here. And so if we wanted to simulate what it would sound like when I'm typing, like if I'm just typing a sentence or a couple of words, and I wanted to simulate that, I'm going to basically take the sounds, line them up one at a time, run them through the model to classify each sound, and we're going to kind of simulate me typing. And so the thing that we're going to simulate me typing is all the way to the bottom here, right here. So Hello, so it's basically look at the first character, space, so the space bar, People, so hello people. And we're going to pass that through our classifier, and we're going to see what kind of results we get. So let's go ahead and run that. So you can see here, Hello space, and then I did a top K equals 2. So you can see in the first column the most confident score. So believe it or not, for hello, Hello, it is the most confident predicted letter. Some of them range from 48% to 69% and so on. The space bar, now what's interesting is right here, OEOOLE. So that's obviously not people. But I picked the top K of 2 intentionally because the P happens to be the second guess. Now, if I'm simulating typing, and we go ahead and we run this through with top k equals 2, we actually have everything we need in order to guess what the message is. So how would you go about then decomposing the problem? So you can, and what we're going to do is we're going to take each one, and we're going to create every possible combination and brute force this thing. Now, it turns out that that's probably not ideal, because that would be, what is it, 6, 12? So that would be 2 to the power 12, which that's how many combinations we would run, and that would not be great. And so how can we potentially chop this problem up? And the big hint is, what key on the keyboard is distinctly unique from all of the other keys? Come on, someone say it. The space bar, 100% right. So the space bar is typically very massive, and it will probably, more likely or not, give you a unique sound different from all the others. And so if we delimit words using the space key, we can now decompose this problem into something that's far more manageable, right? So use the space bar, use the possible combinations for the first 5 letters. So now we've reduced the problem to 2 to the 5th power, which is 32 combinations. It's far easier. Then we look at the next one, people, 6 letters, do all the different combinations, 2 to the 6th power, 64 different combinations, far manageable. So now we have to figure out how can we do this without me looking at this. And so the first thing, and these are all of the improvements, by the way, that I made. So when they did the research paper, they only looked at top k equals 1, which was the mistake. So you need to consider 2 and 3 possibly. And so if we wanted to further improve this, and we don't want to actually manually trying to figure this out, one thing we can do is we can just run the different combinations, use an online service to do spell check, and tell us which ones are actual words, right? And so that's what we're actually going to do. And I'm going to do this live. We'll see how this works. So we're going to run python2_spellcheck. I'm literally going to hit the internet, test every possible combination. For ones that are perfect matches, we're going to just dump it to the console and just print it. And then we're going to see some other cool different permutations, but let's go ahead and kick this off. So here you can see the problem, right? Hello, people. And there are 2 word segments because we're chopping this in half using the space key. We're running the first 5 letters, and at position 5, 32 different combinations, and we can already, based on our spell checker, determine the hello is a word, right? Now, it's going to take a little bit of time, and what it's doing right now, it's giving me the other probable words that could potentially, so we're using the other combinations, we're going to run them through the spell check, and we're going to try to determine other words that they could be. Now, this is ideal because the spell check happened to be exactly that word, so this is why I'm flagging it like as a special combination, right? And so hopefully in a second, oh, there we go, right? We can see the different other combinations with the probabilities and like what we think that the other words could potentially be. So what's really interesting to note is I can make a further improvement, but I didn't do it, is we know that hello, or the delimited word is 5 characters. We can junk this word, because it's not 5 characters, right? So HELLO, and we'd only need to consider these ones. So that would be like a further implementation, improvement. And we can already see that it's chopping away. I'm not going to let this go because it takes a little bit of time because it's checking all the 64 different combinations. But we spell checked, we already hit a combination where the word is exact and it's people. So hello, people, right? So it's actually completely doable to determine what someone's typing using multiple known keyboards. And oops. So, who's heard of the game Mad Libs? I know it's like an old, I should tell you how old I am. It's an old game, 30 years ago. But the idea of Mad Libs was, hey, you have, right, a sentence, you have a bunch of spaces, and kind of the game was that you give me an adjective or a noun, and you ask your friend, give me an adjective, give me a noun. And the idea was that they don't know what the sentence is, completely random. You give them adjective, noun, and it basically creates this massively funny sentence, right? Because you don't know the context of the sentence. So I thought, and I took this idea, and the idea is, another improvement is, every once in a while, the thing is not going to spell check correctly. As you're typing along, it's delimiting, it's checking words. And for those instances where it doesn't know, or it came out incorrect, obviously, the idea was to basically chop or remove that word, intentionally leave a space, take the context of the sentence, pass it through AI to predict the most probable word. And so let's go ahead, and it's still running. It'll never finish. It's just the internet. It's all good. So let's go ahead and do that. And I'm just gonna show you an example. So this one takes a lot longer to train, but I did create a safe tensor format model, which you can download that does this. We're going to run inference only, but you can see the data preparation and distillation training step. But we're going to run, 2 sentences through. And I might as well just run it. It's okay. Because it'll be immediately obvious. Python, inference. So we're going to run 2 sentences through, intentionally leave a hole, right? Fill in the blank. And we're going to use the model to say, hey, what's the most probable word in that location? So if we take 2 sentences, the capital of Denmark is blank. And then the most probable word, top K equals 5 here. Most probable word is Copenhagen. And then we take distilled models are the blank of large models. Top K equals 5, smallest. So kind of the idea is we're going to screw up trying to figure out what these words are, but we might have a helper that if we don't get it, we can blank the word out, run the thing through a model to basically guess the most probable word, and voila. We have a completely autonomous way of determining keystroke sounds for someone typing a Word document, for example. So the results from both experiments. So the single keyboard, the accuracy was 100%, right? Now the multiple keyboards, if we take all the test data, run it through, it's only able to guess what it thinks is the most confident score. It's only able to get that 46% of the time. Now in typical machine learning world, that's actually horrible, right? It depends on the number of things that you're trying to classify. But in this particular case, that's actually pretty good, because if you were to randomly guess any of those letters, pass it in through the model, you have a 1 out of 38 chance. So now 46% doesn't sound bad, and that's the reason why we include, hey, what's your second guess, or what's your third guess on that letter? And so if we do top K equals 2 or 3, we do all the different permutations, we chop it up, we've used the fill in the blanks. Now we have something that's actually solvable. So one thing I did not test, which I did actually in the sarcasm detection classifier session, which is the video I included in the front, is independent data sets. So this is the idea where we build the model, but we're introducing a whole new foreign keyboard that the model has not seen before. And I did not do this. In the sarcasm thing, it actually turned out to be okay. But in this particular one, I kind of just said, I'm not going to do it, because I already know that this is probably going to hit that 3%. So the saving grace in everything is that these are known keyboards, right, that I'm building this. I can't just take a keyboard off the shelf and then test it and come back and classify it. But I think this might work. So manufacturing similarity. So if we take 2 different keyboards from the same manufacturing lot, and we let people type over time, and when people type, they tend to hit letters at certain frequencies. And on the little thing here, and this is for the English language, right? So you tend to hit the letter E far more frequently than every other letter, than T, A, O, right? And so the idea here is, which I did not try because I didn't have a data set to do this, but the idea here is that the wear and tear on the keyboard is pretty uniform. And if you were to take the same keyboard in the same manufacturing lot, I'm guessing I would be willing to bet that if you were to take a new keyboard in the same manufacturing lot that's run through a couple years of everyone typing, that this would probably work. So, what are some other improvements? Not that I'm trying to horrifically make this thing, So, what are some other improvements? So, when we did the sounds, we captured the sounds independently. So, there are other potential improvements that we could make. So, we captured the sound like this. Now, that's not how we naturally type. So typically, a lot of people put their fingers on home row because it's typing classes that we all did a long time ago. It's faster for us to type. So maybe take typing flow into account. Maybe get multiple users because some people are heavy-handed when they press, and some people are more light. So get sample representative data to start to filter out the non-relevant stuff so that you get even more narrowed in on what those sounds are unique for those letter presses. So I don't do home row. I like peck. I don't even look at the keyboard, and I just know where the letters are because I've been on the planet for a really long time. So that maybe this, the current method might actually work better on me than someone who might be using home row. Again, just throwing ideas out there. So real-world attack vectors. So this isn't a new thing. So a long, long time ago, there used to be this toy in Captain Crunch, if you guys remember people remember the cereal. And it turns out that that sound, the frequency of that toy, that whistle, when you blow into it next to a payphone, you would get free phone calls. And so that's because our payphone systems were all sound acoustic based. So there are definitely ways of hacking things using a sound, and this toy was definitely proof of that. So it went on for decades like this. So if you happen to know that frequency, you could get free phone calls at payphones because the dial tone, right, is all sound-based. So if we were to take what we know now and apply it to a real-world problem, so what single keyboard could we use to target, to build a machine learning model? And when I thought about this, I immediately thought of this. It's a keyboard that's fixed. Everyone uses it. You could go up to the ATM because you happen to frequent the bank. That's your bank. 1, 1, 1, 1, record the sound. 2, 2, 2, 2, record the sound. Capture enough sounds, and you have a machine learning model. So further improvement on that. So how would you know when to start collecting the sound? Who knows what a credit card skimmer is, right? I think a lot of people know. When you this is what a credit card skimmer goes. It fits over the face of the credit card, so when you put it in the slot, you get a copy of the magnetic signature. That would be your trigger to listen. And now you can tie the magnetic signature to the pin on the keyboard. Don't do this at home. So how would you attack multiple keyboards? So everyone has probably, it doesn't require your laptop to be running or logged in, but everyone has their keyboards. I flip it open, I just hit the button on the keyboard, they're just lying around. If you're wanted by the government, I'm just saying, they could get a keyboard and go into your house or whatever and hit the keys or whatever and build something to listen for what you're typing. So just understand. So now that I've scared the crap out of everyone, how can you protect yourself against this stuff? So this is pretty obvious, right? So two-factor authentication is a great way. So I have a YubiKey. I actually have 3 of them for depending on like what they are, like what, I don't trust my work, so I have a different YubiKey for that. So use that, because even if they were listening and typing, like you still need the YubiKey to like open your password file or whatever, right? A lot of 2-factor authentication, they have SMS. I would not use that. It's not safe. If that's the only thing that's available, that's better than nothing, but it's not safe because of femtocells, fake hotspots. Basically, the idea is that your phone is closer to a fake hotspot, and you can, basically the owner of this fake hotspot can like listen in on everything that you're typing or doing, or all the traffic going back and forth and all that fun stuff. So don't do that. So here's a pro tip. If you've ever changed the password on a wireless device where, you don't have an interface for it because it's like an IoT device. Like as an example, I have a smart garage door opener, and I log into the smart garage door opener app and I change the password, and you hope it works because you change the password on your router and it doesn't work. And I'm trying to figure out and debug what the heck's going on. I actually take my hotspot on my phone, set it to the same username and password that my router was, so that I can hopefully have that thing connect to my cell phone, which is much closer, so that I can log into the app and still connect to the garage door opener. That is a very ghetto femtocell, right? Use passwords you don't know. So it's better that you don't know your password. That sounds like a weird statement, but it's true. And so use services that generate passwords for you. I would recommend not using an online service. Everything online will eventually get hacked. So I use stuff that's offline, right? So that it's not connected to the internet. And the reason why you use passwords you don't know is because they can't socially engineer the password based on your favorite football team, what your son or daughter's name is, the year they were born, all that stuff, which drastically reduces the number of permutations and combinations for your password, right? Have a different password for every platform. So, if you use the same, I hope not, if you use the same password for all your banks, your banking system, like maybe you have multiple accounts, if one gets compromised, all of them are potentially compromised. So have a different password that you don't know for everything. Change your password frequently. I know that sucks. Every 90 days your employer usually says go change it, but I mean that's kind of the idea, is like rotating passwords that are like 32 characters in length that are next to impossible to crack. And then be intentionally difficult. So I actually was going to embed a video in here because there was a great scene. Who remembers the TV show Alias, like 2001? So it's a great spy TV show. I was going to embed a video in here because I remembered there was an awesome scene where the character's name is Sydney Bristow. She's a CIA agent telling her boyfriend, who wasn't in the know, that she was an agent. And she goes, and I thought it was, they were sitting, and she turns up the radio. This is like episode 1, the pilot episode. And it turns out it was in the shower, the water is going, and it was a little too racy to put in a video to demonstrate interference, so create noise or something that could potentially interfere with sound, right? And the interference patterns, or maybe even noise canceling. I don't know, noise canceling for sounds, right? So I know this is very tinfoil hat sounding. And this is a news article that hit this year, January 29th, 2026. Apple acquires a startup QAI. Using a wearable, this is a patent in the United States, using a wearable to interpret facial skin micromovements. So when I saw this, because of my tinfoil hat, because I'm very security-minded conscious, this is what I thought of. Microfacial movements, so you could detect what you're saying just based on your face moving and your mouth, your lips, all that stuff, right? So lip reading. And you think I'm paranoid? one reason why maybe Apple wants to start putting cameras in their earbuds, and they are, right? It's coming out this year. Just be aware that cameras are going to be everywhere. So resources. So everything. And the reason why I'm talking about all this is how to keep yourself safe. You use the models to understand how to disrupt this stuff, right? That's the point of this. So everything to train the models, the data sets, do the inference, if you want to build the masked language model to guess the holes or the most probable words in sentences, you can find that all on that GitHub repo right there. And if you're interested in the research paper, you can see the research paper, the original data sets. If you're super interested in nerdy AI, ML stuff that's security conscious kind of, I did a talk at We Are Developers last year. It was called Confuse, Obfuscate, Disrupt, and it was basically introducing intentional mistakes in order to disrupt AI to get them to do things that you want to do. So as an example, misclassify something, so text-based. So if you're trying to get around, I don't know, an example is an Amazon review ML classifier that's trying to detect negative sentiment. That one's for you. And if you are just interested in that AI dev, what you're doing, detecting sarcasm using machine learning model, there's that session there too. Those are recordings to those things. And with that, thank you.